All right, things get a little more complicated when we start looking at the end of a tank or a vertical plate. And the reason is the pressure is higher at the bottom of the plate than it is at the top. And so to deal with that, we have to use our what's by now a pretty standard technique for integral calculus. We want to divide the thing up into a bunch of narrow pieces and then find the force on each one. So the idea would be, let's say this is either the end of a tank or the outline of a plate. What we would do is draw in a little strip across here, representing just that little part of the end or the plate right there. We'd call the thickness of it dx or d something else. We'd find the force on the strip, and then we'd have to integrate from the bottom to the top to get the total force. Now you might say, how do you find the force on the strip if it doesn't have anything directly above it? And the answer is Bernoulli's principle. I'm pretty sure that's what it is, Bernoulli's principle. But the concept is, if you've got a point here underwater, the amount of force that's exerted on it from this direction, you could think of it as being exerted on it from other directions as well. So the thing that we need here, this is how I memorize these problems, is force equals AD rho G. Where A is the area of the strip, D is the depth, and then rho G is the density. It's either 62.5 or 9,800, depending on whether you're doing feet and pounds or meters and newtons. So let's look at this first example. Find the hydrostatic force on one end of a full aquarium that's 2 feet tall, 3 feet long, and 18 inches front to back. All right, so it's 3 feet long, 2 feet tall, 18 inches front to back. I don't know that my drawing here is very well to scale, but it doesn't really matter. So we're trying to find the force on this end. Let's label this. It's 3 feet long, 2 feet tall, and 18 inches front to back, so that's 1.5 feet. So the strip that we're going to be looking at is going to be across here. So I'm going to redraw just the end of the tank. So this is 1.5, this is 2, and the strip goes across here. Now the little thickness of the strip here is dx. So let's look at this. The area, I'm going to come up here. Actually, before I say that, this is all just for the strip, not for the whole end of the aquarium. For the strip, the area is 1.5 dx. It's length times its very small width. So area is that. The depth, now you could choose to do the depth in a couple of different ways. Actually, no, you need the depth to be this up here, how far it is from the top of the water. So the depth is x, and let's see, rho G, in this case, since we're dealing with feet, rho G is going to be 62.5. Notice one thing, it's important here, since this is in pounds per cubic foot, it's important to call this 1.5 feet. Don't leave it as 18 inches. That'll mess things up. All right, so for the strip, you get all that, and so the force on the strip is going to be just the product of all that stuff. 1.5x times 62.5 dx. What is that? 1.5 times 62.5 is 93.75 x dx. And so the total force is going to be the integral of that from 0 to 2. Because we're going from the bottom of the tank to the top. Actually, we're going from the top of the tank to the bottom. The reason is x is our depth. So up here, this would be where x is 0, and down here, this is where x is 2. All right, so this is a fairly easy integral to do. 93.75x, divide that by 2. So when you integrate this, you get 46.875 x squared from 0 to 2. And I'm not going to write this down. I'm just going to plug in the 2 and get our answer. So 46.875 times 4 gives me 187.5 pounds. Like that. All right. This next example we'll do in the next video.